Hello, everybody, and welcome to our new online technology meeting. My name is Antonio Castelo. I'm technology manager at EPIC, in charge of all the laser-related technology and also the bio and medical markets. And I'm very pleased to be here to talk about additive manufacturing. That is a quite interesting technique. We had a boom a few years ago, and I think we still have some applications that need to be addressed. Some interesting developments that we need to discuss. And today we have a great set of speakers to talk about them, also about the challenges and needs still present in the industry. Just a few words about EPIC in case somebody of you doesn't know us. We are the European Photonics Industry Consortium. We are an association of more than 100 members, all companies related with photonics technologies. And the goal of EPIC is to ensure the sustainability of the photonics business by connecting people, so everybody can find partners for collaborations, can increase the business opportunities, and can also know more about new markets and applications for the technologies. And as you can see here, this year is our 20th anniversary. We are quite happy that we will have a very nice party in Laser Wall of Photonics that I will let you know when is the date at the end of the session. Some words about what can we do for the members. So as I mentioned, we are the industry consortium of the staff of EPIC, can help all the members with the technology request. So any need related with the technological point of view can be a need on a new partner, can be a need on a new supplier. We can help our members to find some options. We have also access to give access to market reports to our members. We organize also different activities to increment the networking of our members, like this kind of meetings or our in-person meetings. So the idea is to connect people to give them more opportunities to grow. There is the possibility of access to markets and also to mentors. And we also help with human resources and also investment for the companies that need money and also for the big companies that are ready to invest. We are also involved in different European Union projects. You see here all of them, JEPIX, Method, Multiple, Fabulous, PhotonHub, and Pulsate, that is the project that is supporting the event today, is a pan-European network for helping SMEs and all different companies in introducing laser-based advanced and additive manufacturing in their processes. And this is the agenda for today. So we will have a very nice speakers, as I mentioned. We have different topics from the traditional, more additive applications to process monitoring. We will also learn about new printing technologies and also about materials, new developments in materials. So thank you to all the speakers for being here. And I will let them know when is the time to present. And this is the picture of all the companies that are present here today. As you can see, we are covering most of the supply chain or all the supply chain, different components manufacturers that are interested for developing the machines. Also the proper additive manufacturing solutions and machines. We have different companies that are involved on that. We also have companies doing semiconductor manufacturing, service providers, for those of you that cannot afford buying a machine and need help to develop a project, and also the important end users, of course. We see that additive manufacturing is interesting in different markets, so we can see end users from aerospace, eyewear, automotive, consumer electronics, and also semicon. So it's very interesting to have all this picture that you will see later on in our website. In case anybody of you want to be contacted with one of the persons registered to our event, just let me know, contact me back, and I will introduce you so you can discuss in private your needs or your ideas. So the next step is to help to say thank you to our sponsors, of course. We will start with the sponsor Optocraft, that is our partner. And I don't know if Christian are you here in the room?
Yes, I am. Hello, can you hear me?
Yeah, we can hear you. So perhaps you can say a few words about your company at this moment.
Yeah, thank you for the occasion. So we are manufacturing and developing shock Hartmann wavefront sensors And these wavefront sensors are used to measure the quality of a laser beam, basically, and also for optics alignment. But I think in this audience here, the laser beam testing and alignment is quite interesting, because each system that is used for selective laser melting, or also other laser manufacturing processes, each system, as you know, creates a focus, and you need to control the position of this focus very precisely. And the wavefront sensor can help you to control this focus position. So basically, these wavefront sensors can be used for an inline monitoring of the optical system that is used in laser materials processing systems. This is a nice application. As you can see, these wavefront sensors that we offer are relatively fast. They have a good stability and can be used in a broad spectral range. And this is what I think makes this technology very interesting to this audience for integration into the machines. So yeah. Maybe there's one or the other who might be interested, then feel free to contact us.
Yeah, that was also my last phrase. Chris, you can contact Christian if you are interested in their technology, or contact us if you want to be introduced to them. We will be glad if somebody's interested in their technology. And thank you very much for your support in this event.
Thank you.
And our next sponsor is Near Infrared Technologies. They are not here because there is a bank holiday here in Madrid. So it's the main holiday in Madrid. So I understand that they are enjoying the free time in the sunny countryside. But they sent me this slide, so you can see what are they offering. They are a company located in Spain, developing and commercializing industrial solutions for real-time process monitoring and also smart control of industrial processes based on their mid-wave infrared and cooled infrared cameras. And they want to promote mainly their solution called Clamir. It's a system designed for quality assurance of laser direct energy deposition processes like laser metal deposition or laser cladding. This Clamir solution is based on an embedded system with a medium infrared camera, an imaging processing algorithm to extract the dimensional features of the melt pool, and also the control electronics to control laser power. All the processes are done in real time inside the camera, and it is fully compatible with most of the laser optics and powders. It is integrated mechanical and also to configure and guarantees consistent operation without reconfiguration during the process. You can see in the video how the system is working. Is based on the medium infrared image acquired in real time, looking to maintain the melt pool width as stable as possible. So the laser power is regulated by the control unit through the analog output. And the system was awarded, as you can see, also in 2018 with the Innovation Radar Prize in the category Industrial and Enabling Tech by the European Commission. So also please contact us if you are interested in having more information about the solution, and we will be happy to put you in contact with them. So thank you to Optocraft and Near Infrared Technologies for the support today. And we can start with the first presentation. We have from CATEC, the Center for Aerospace and Technology in Spain, Fernando Lasagni. He's CTO of Materials and Processes. He's going to present the metal additive manufacturing for the space industry, trends and certifications. Just to remind you that at the end of the presentation, we will have time for question and answers. So please feel free to raise your hand and make your question directly to the speaker. So Fernando, the floor is yours.
Thank you, Antonio, very much for the introduction. Okay, you should be working right now. So
yeah, perfect.
Well, the idea of this talk is to give you three different issues which are related with the manufacturing of metal parts for the space industry. How parts are certified, qualified, and also few of the most relevant projects we have been developing in the last years in the sector. So first, I would like to give you a few introduction of myself. I'm the Chief Technical Officer on the Materials and Processes area at CATEC, working for many years in the sector. Also having the representation for Spain related with the harmonization meetings at the European Space Agency, and yeah, different hours which have been granted in the framework of the technology. Now coming to CATEC and to the presentation again, I have to say that we have been working in the past with many different customers. CATEC is a research and technology organization, so our main focus is to develop technology for the industry and the technology transfer, which include as well prototyping. And in case of space technology, many of these demonstrators are finally implemented in different missions, because it's of course a difference, which is space, for instance, from aeronautics, where serial production in space, we are talking about few parts, and it's not the case of other industries like aeronautics, the automobile industry, and so on. So we have plenty of collaborations in the framework of metal additive manufacturing with different companies here in Spain and also in Europe. And in the last year, we have been working in several application cases for launchers, satellites, spacecraft, and also rotorcraft or commercial or military aircraft. This can be deployed better on this slide, where in a timeline you can see different projects we have been working on. As I said before, many for launchers applications, satellites, and also spacecraft. In the first projects, we were working in the validation, qualification of the technology, also producing functional demonstrators, which has been validated in a high TRL. And with this experience, we start to manufacture flight hardware. A few of them I will present today, not only in the space, but also in the aeronautic industry. For the last one, for instance, the first critical parts, which has been introduced in an Airbus rotorcraft, were manufactured in the framework of a European project. Titanium parts belonging to the top fittings of the tail unit of the helicopters, also some other parts belonging to the secondary structure, or for instance, different failings for the Clean Sky 2 demonstrator, which is a modified C295 aircraft, which is assembly here in Seville at Airbus facilities. So where we are talking about additive manufacturing, of course, there are many different processes. It's not only the manufacturing steps, it's adapting the design for all the spot processes and the inspection as well. That's where we have a huge expertise. And yeah, for qualification, certification of the technology, there are many different issues which have been validated, and there's quite a lot to do also related with the post-processing, because at the end you have to demonstrate that you have the capability for producing the complete value chain and yeah, delivering a hardware with the required quality. So now if we think on what has been done in the last years on the sector, basically, for instance, you can find different standards which are coming from the space agencies. For instance, this one here is related with powder bed fusion manufacturing, also laser beam or ion beam technologies. In this case, of course, for producing space hardware. There are, of course, different standards from NASA, which is other relevant space agency in the world. And later, there are also many different specifications coming from the large OEMs. for instance, Revaz, when they will provide you more specific details, and most relevant is the which will be the allowables for qualifying your component. That's, for instance, in terms of mechanical behavior and so on. So basically, there is a huge list of processes which must be addressed. Of course, the manufacturing, and then all the post-processes, the finishing methods, the thermal treatment, how parts will be inspected, and so on. And all this process also and requirements will be adapted, which is to the criticity of the parts. For instance, in space, we have mainly 4 classifications. We have critical and structural parts, critical but non-structurals, and then non-critical but structural, and finally non-criticals and non-structural. Basically, under this criteria, we are classifying which is the impact of losing a component, a tech manufactured component, on the space mission, how the mission is affected, how the spacecraft is affected, and in this way, we obtain the final classification. Similar to this criteria, there can be found some other requirements from the large operators, which basically refers to the same characteristics. Okay, so a few examples of what they have done in the past. First is the development of support structure for the quantum satellite, where, of course, the losing of those supports means that we lose the solar panels, so they are critical and structural, all these supports. Then, case of the JUICE spacecraft, we have, for instance, secondary structure. In this case, we have for instance, the brackets, the supports of the mission sensor. So we don't lose the spacecraft, but let's say the functionality of the mission is of course decreased. So they are not critical but structural. And in some other cases, we have developed, for instance, for the key of satellites, some non-critical, non-structural parts, which are basically part of the satellites, which has been used for assembling issues, but later they have no service during operation. So since they are attached to the satellite, they have to be classified somehow. Going to the process, well, we will work on different steps. First, we have to, let's say, qualify our system. We have to produce different samples in order to check which are the characteristics of the material I'm producing. And there will be criteria, requirements for tensile or fatigue testings, even in space, and not a large number of cycles, but this is also criteria. And then will appear some other characteristics like fracture toughness, also thermal conductivity, when we are developing antennas or products which requires such kind of functionality. Also CTE, there are many different requirements we will apply, and our operator will define which are the allowables. For instance, which is the minimum tensile strength that we have to achieve in order to qualify our system. In this case, with many different issues. Also, there will be some requirements related to the powder. And also, since this is raw material that we will reuse and recycle, also there will be requirements for monitoring, process monitoring of the reuses powder and so on. So basically, the standard for ESA in this case will determine which are the process which has to be monitored, and later the allowables are defined by the final customer. So this is which is related with the qualification of the system, but then when developing a new product, we have requirements also at prototype levels. Sometimes we can use the prototype for flying directly. Depends on many things, the maturity of your system, your experience, and also if there are similar parts that have been produced before. This is a negotiation with the customer. And there we have to evaluate different issues, taking into account entity, of course, dimensional, control of the parts. And then we will have to do also mechanical tests just to monitor if we can reproduce the same mechanical properties and so on. So this is very important step. And with this information, what I will pass is the so-called manufacturing readiness review, where I will specify in detail how the part is manufactured, how the system is controlled, how I will do the inspection, how the part is supported, which are the thermal treatments, and so on. So just, yeah, then I will have, for instance, also criteria in terms of inspections, will be also related with the criticity of the parts. Basic technology for inspection of metal hardware right now is X-ray tomography, and this is a requirement, for instance, in critical parts. And yeah, there are different issues I have to cover. Sometimes I will need to do functional tests or not. That will depend on the criticity. I want to go very fast because I'm out of time, but just to show very rapidly different application cases, as I said before, supports panel, support structure of the solar panels of the quantum satellite. We are coming from optimized design, no topology optimization, but reducing the way by making some taking some advantages of technology with comparison to CNC. So here we have, for instance, how this supports a manufacture, and finally, after post-processing, in this case, machining of the interfaces. This hardware was launched in 2021, and then also now applying topology optimization in collaboration with CITD, engineering company in Spain. We are able to develop this supporting structure made of scalum alloy, achieving a reduction of 50% in weight, and also reducing the numbers of parts from 4 to 2. We have been fully validated and qualified for flight with final tomographic inspection, for instance. Together with CNR, we have working on the development of a helix antenna in aluminum silicon magnesium alloy, which is produced in one shot. Again, all post-processes must be warranted. You see in the image also samples which are used for monitoring the manufacturing and finally tests, and finally going through all the qualifying tests, RF, vibration, shock test, etc. This is integrated in Proba 3 and will be launched in short time. I'm finalizing what we have done for the Jupiter Icy Moon Explorer, which is one of the most important missions of ESA in the history of ESA, where we have manufactured part of the secondary structure of this mission is going to study Jupiter moons, where we have liquid water, and with the possibility of finding life in the moons. And it's a very complex mission because it's using gravitational acceleration to reach the Jupiter orbit. And for that, sometimes we have to come back to Venus, where we have the twice radiation than in Earth, but in Jupiter we have only 3% radiation than in Earth. So that means many very relevant thermal gradients, and also some Jupiter moons are magnetic, so we have also to deal with that. And in this case, we have manufactured, which are the sensor brackets. Many of them in scalum alloy. It's a joint project we have done with the engineering company CITD, and also which are the reaction wheel breakers and antenna supports. So this mission has been launched last April, and now it's in the way to Jupiter. It will take 8 years to reach the planet. You see one of the supports of the sensors in the wheel plate, and after post-processing, and also integrated in the spacecraft. And yeah, this is something, as I said before, we have the launch of the mission. Our video is not working in April this year. So I'm out of time. So I want to thank you, Epic, Antonio, for the invitation, and yeah, open to questions. Thank you so much.
Thank you very much, Fernando. Really interesting, and thank you for summarizing all the needs and all the requirements, and also a summary of all these projects that you have been working on. We have time for questions, so as I put in the chat, raise your hand and make your question directly to Fernando. I can perhaps start with one question. Is in all the projects that you face up to now, did you miss something in terms of the technology? Can be that a specific material that could be better than the ones available nowadays commercially for one part. Perhaps the technology that you use is not the best one and you would like to have another technology. Did you miss something in a part that perhaps is not as good as you would like?
Mm-hmm. Yeah, it happened quite a lot in the last years, actually. For instance, there was no really specific aluminum alloys for additive manufacturing. 10 years ago, we were using this aluminum silicon 10 or silicon 7 magnesium alloy. And later, Airbus came with the Scalm alloy, which is an alloy which is designed for the technology, having much better mechanical properties and performance. But now, for instance, what we are seeing is quite a lot of development in terms of, again, aluminum alloy, but having much better electrical or thermal conductivity, which is a requirement for many different space applications. So we are tackling, for instance, which is the qualification of such kind of alloys in different projects. Yeah, later, of course, there are many other alloys coming. It is very important what is done right now in titanium, not titanium 64, titanium for additive manufacturing, and this is something which is happening right now. Regarding the systems, well, the monitoring technology is really a must, but monitoring technology which can give information not only on a frame on the which you take from the top of the wheel plate, something what is happening below that. And today we have a presentation about that from Bernard, I think, which is very important. This is something which can be useful in order to decrease inspection requirements. Sometimes when we are manufacturing critical parts, depending on the size of the defect on the allowables, we have to perform several tomographic inspections, and that, of course, increases the cost of the part quite a lot. So whatever is coming in the framework of monitoring would be very interesting.
I don't know if there is any question. I have another question for you. Is perhaps a question thinking in a manufacturer of additive manufacturing machine, because you talk about certifications, all the process that is needed to put the part. Must an additive manufacturer, additive machine manufacturer, be aware of these kind of certifications, normatives, and so on, if they want to go into the aerospace, or is something that the aerospace company is already aware of, and they don't need to have this kind of knowledge?
Yeah, manufacturers know about that. But they usually do not, let's say, they do the qualification procedure, so just work in collaboration with customers in order to help them for the qualification or certification process. This is how it works right now.
Okay. So thank you very much. If there is no more questions for Fernando, thank you very much for all the information you shared with us. And we can move to the next speaker. We have Wolfgang Hauser, is research group leader at the UANIM Research. We are moving to the medical market, and he's going to present challenges and opportunities of metal 3D printing for medical applications. So Wolfgang, the floor is yours. You can share your screen.
Good afternoon, everybody. Thank you very much for this nice introduction. I will now go to the presenter mode. So yes, I think you can now see my slides. Yeah, my name is Wolfgang Waldhauser. My background is material science, and I am research group leader and key researcher at UANIM Research, and I'm leading the research group for laser and plasma processing, and I will give you today a short presentation on metal 3D printing for medical applications. But at first I will start with a very short introduction of our company. So we are a non-university research organization. We have about 500 employees. We have 7 institutes. We are located on 6 different locations, and here you can see also our owners. So the main owner is the government of Styria. That's one of the federal countries in Austria. And here you can see our 6 institutes. So we are working very multidisciplinary. So we have one institute for digital technologies, then the Institute Materials, where I am coming from, so Institute for Sensors, Photonics and Manufacturing Technologies. Then we have one institute for robotics, one institute in the medical field, so for tissue regeneration and wound healing, then also in the field of medical science, our Institute Health, and then the Institute Life, and the center, our Institute Policies. Yeah. And as mentioned before, I am leading this research group, laser and plasma processing, but we have at our institute also other fields where guys are using optics. So for instance, here we have the group light and optical technologies, or also our group smart connected lighting. So our institute is led by Professor Hartmann. We have approximately 100 employees, and here you can see our main areas, but I will focus on the laser and plasma processing. So what we are doing, we have 2 main topics. The first one is the laser processing methods with high power lasers. So we are working on laser welding as a joining technology. Then we are working on 3D laser metal deposition, or also called as LDED process. We have strong activities in selective laser melting, so laser powder bed fusion. Then we have laser cladding in our institute, and we are also doing laser alloying. This is a very unique technology. This is not very well known in industry. So we are using the laser beam as the energy source to locally mold the material on the surface of components, and then we are adding powders into the melt pool, and so we can generate locally a new material with new microstructure, new properties. Then we are doing, of course, laser beam analysis and metallographic characterization of the parts. And in the second field of our activities, we are focusing on the plasma surface engineering. So we are developing functional coatings for different applications. We are using physical vapor deposition as one of the technologies, then plasma enhanced chemical vapor deposition, but also plasma polymerization, and also a so-called atmospheric pressure plasma coating technique. And of course, we are also doing intensively film characterization to know the properties of the developed films and to find yes, the suitable applications for these coatings. Yeah, what we are doing in additive manufacturing, so we are doing applied research in selective laser melting. So we are performing parameter studies and process development for metallic materials, for instance, titanium alloys, but also aluminum alloys, nickel alloys. In medical field, we are also working on metallic glasses, so a special zirconium-based alloy, and we are also doing, especially this is the next step for the future time, working with composites, so a metal matrix with ceramics inserts, but also composite materials. So the combination of different additive manufacturing technologies, for instance, for the metal, the laser powder bed fusion, and then to join it together with polymer parts. This can be done with the filament based technologies. Yeah, we are also doing simulations of additive manufacturing processes and parts. So we are using the ANSYS software, so we can simulate temperature distribution during the printing process. We can also get information on the intrinsic stresses and distortion of our parts. And also that's planned for the future to simulate the microstructure which we can achieve in our processes. Yeah. We have also, as you can see here on the scanning electron microscopic pictures here, activities in post-processing of additive manufactured parts. So we can compare different techniques like glass bed blasting, sandblasting, together with partners. We are also focusing on to electrochemical surface finishing technologies. And our main goal is always, because we are focused on to applied research, to open up new fields of applications. And these fields are aviation, as we have heard in the presentation before, then also tool technology, and I will focus in my presentation on medical technologies. So you can see here, for instance, some radius plates printed with powder bed fusion, and here the application of these plates in the human body. Yeah, important when you are working for medical implants is to consider the whole process chain. So we are now in a relatively big national project for printing of medical implants. And so we are starting with the material selection. Then the next steps are finding the optimal printing parameters. This needs very intensive characterization of the powders, but also of the microstructure and porosity of printed samples, and of course also to investigate the mechanical properties. Surface finishing and post-treatment, like heat treatment, is also very important. So here, for instance, you can see the difference. This is the S-printed area of a radius plate, and here after electrochemical treatment, yeah, a so-called hertization process was here used. Together with our partners in this project, this is the Medical University of Graz, we are doing cytotoxicity tests and other tests to check the biocompatibility of the materials. In some cases also antibacterial behavior is important. And then the next steps is to perform biomechanical tests here of printed radius plates. At first, this is done in a laboratory with sawbones, but then it's also planned to do it with human bones. Yeah, and the last step is the clinical studies of such tests. This is performed by our medical partners. And here in this project, which will be finished or finalized by the end of this year, the goal is the comparison of printed plates with conventionally fabricated plates, because such plates can also produced conventionally with milling and so on. But here our approach is to show that printing of such implants leads to the same properties and qualities. What we are planning for the future, we are now in the conception of an Horizon Europe project. So the goal of this project is also to develop the scientific, technological, and medical basis for the realization of load-bearing implants, and what's new, to use on the one side non-resorbable materials or metals, and on the other side resorbable materials, and also what's new, to implement suitable sensor technologies into the implants or onto the surface of the implants. Yeah. So our approach for this project is to develop composite implants. So it's planned, for instance, to have a metal core and then a shell made of polymer. Yeah, we have to develop the printing processes for the non-bioresorbable and the bioresorbable metals and materials, and then the integration of sensors. And this is based on a PiezoFlex technology. So it's an piezoelectric material which can be printed on thin foils or directly onto the surface of the components, or in our case of the implants. This is a development of Joanneum research of our sensor group, and the goal is to detect deformations, to detect vibration behavior, and also temperature. And so we want to investigate whether we can get informations on the loading of the implant, also on the ingrowth behavior, or also by detecting the temperature, we should achieve information on inflammatory processes in the surrounding of the implant. Yeah, and in the case of bioresorbable implants, we have the idea that by measuring the vibration behavior, we can achieve information on the degradation process of the implant. Yeah, and it is planned then to develop also a digital twin of some selected implants to get information for the future, and to develop very efficiently new implants, and yeah, of course also to know when it is necessary to change an implant or when there are some problems with the implant. Yeah. So what we are looking for partners on the one side which are interested in the development of functionalized additive manufactured implants. We are looking for partners with expertise in finite element calculations. That's important for design of load-bearing implants. Then also experts in the production of metal powders from resorbable metals for medical applications. We are searching for partners which are interested in our PiezoFlex sensor technology. And this, in our project, it should be used for implants, but it can be also used for other applications. In combination with the sensor technology, we are looking for partners with expertise in the realization of the electronics, which should be implantable, of course. To get the signals of the center out of the human body, it's necessary to have partners for RFID or NFC technologies. Yeah, and also programming and evaluating the software for sensor data. Yeah, and also we are looking for partners which have experience in the creation of digital twins for medical technology. Yeah, here you can see the overview of our group. So we are 26 people working in the topics which I have introduced to you. And so I say thank you for your attention. I hope I was in time with my presentation, and I am open for your questions. Yes, and I hope that we will find for our planned project some partners and collaborations. It is planned to submit this new project next year. So the call will be opened in autumn, and next year we have then to submit the proposal in a two-step procedure. So thank you very much.
Thank you very much. Also, thank you for sharing all your needs for this new project upcoming. As he mentioned, we have time for questions or comments. I have one question regarding this surface finishing, because you mentioned some blasting technologies. Now there are some companies also trying to do laser-based surface finishing. Do you think they could be a substitution for the blasting in the future in the medical, or do you still rely on the blasting, and the laser techniques must overcome some perhaps disadvantages?
At the moment in our present and ongoing project, we have found that for implants, the best qualities we achieved with electrochemical surface finishing. Yes, I think it could be an option to use some laser polishing techniques. It depends, I think, on the complexity of the geometry of the parts, and also on the size. If you have very big parts, I think this technology is not so efficient. It would take a long time, but I think for small parts and small implants, it could work. Yes, we have, or we should check this. Yeah.
Very good. Very good. And I have also the same question I placed to Fernando. In your experience with these additive manufacturing technologies and the projects you face up to now, what do you miss in terms of the commercial available technologies, or materials, or components? Did you miss something in the past? Did you find any problem because there were certain technology not available?
No, I think that when we are focusing on the powder bed fusion for this time, and we have also activities in LDED for bigger parts, but for implants, this is not relevant. So I think at the moment, very important is also is for aerospace applications or aviation to have a good quality control, so an in situ control during the process. So by melt pool monitoring and such technologies, I think should be used. Yeah, so we are planning also to go into this direction and to add some equipment to our printing machines, and we will get, yes, in 2 months a new machine for powder bed fusion, and this will be equipped which has monitoring systems. Yeah, I think this is very important to have really a good in situ quality control during treatment. And also, as mentioned before, it is also important the removement of the support structures. Yeah, this is always in additive manufacturing a problem. We are in discussion with our partners which are doing the electrochemical surface finishing, and they have some possibilities, if the support structures are printed in the right way, that they can also be removed electrochemically. Yeah, this should be also investigated in detail, I think so.
I have one question also in the question and answer box. From Ono van Apeldoorn from SFC Energy. He's asking, which laser do you use for metal 3D printing, and how much is the optical power?
Now we have at the moment 2 powder bed fusion machines available. We have an EOS machine with a laser power of 400 watts. And on the other side, we have a TruePrint 1000 machine with 200 watts laser power.
Okay. We have the same question from Brian Scholl from Wavelength, so both as an answer at the same time. Yeah, I have a question from Cilios. Terry, please. You're muted right now.
Sorry, I didn't unmute my mic.
Oh, okay, Thierry,
Okay.
now we hear you and see you.
Hello. Yes, I've heard that you were looking for a partner for a coming Horizon project. Okay,
Yes.
if I understood. Okay. And currently, Cilios is involved in additive manufacturing project with a power bed laser fusion system procedure, in which this project is called InShape, ENSHAPE. It's a running project that started, let's say, in June last year. And in that project, Cilios does the, so it's headed by TUM, Technical University of Munich. And we have other partners like EOS, for instance, but other also user partners. Because I speak about OS because you said you just had an EOS machine. And in that project, Cilios is doing the multispectral monitoring. So it's providing multispectral cameras for, let's say, the thermal monitoring of the plasma process, So I would like to know if that would be something that could be interesting in your project. That's one point.
Yeah, we should discuss this in detail. Yeah, of course. Yeah, we are interested.
And also, Cilios is also doing laser beam shaping. It's also one of our competencies. We have two competencies: multispectral imaging and diffractive optics for laser beam shaping. And I would like to know if that also other function could be of interest for your project.
Yeah, we have also some ideas to go into this direction in future time, and we are checking if we will do this in this medical project or we will do it in other project. But I think that laser beam shaping is very important to improve the process, especially for some materials which you cannot operate at this moment. Yeah, so I think this could be an option. Yeah, what profiles can you achieve with your beam shaping method?
In fact, we can achieve a very various profile. We work on let's say passive component. Okay. That in fact that can sustain this high power. We worked about, I would say, 10 or 11 years ago on the laser, let's say, kind of additive manufacturing. It was another application with the DTU, the Danish Technical University, and we achieved some different profile. Let's say, of course, the standard top hat, but also the elliptic and also the point plus a ring plus etc. etc. These type of things. We are very flexible in terms of beam shaping, but that I think, if you're interested, I don't know if Antonio, you could exchange our coordinates so that we go on discussing with that.
This would be important. Yeah, we have some experience with different beam shapes in laser welding as a joining technology. So there we have used this bright line method, which was developed by Trumpf, and we achieved really an improvement, especially for welding of aluminum alloys and so on. Yeah, I think also for additive manufacturing, this is a new and very promising way, to improve the processes.
In terms of shape for welding, yes, we did some works also, but it was for cutting, not for welding with Trumpf on the 8 kilowatt CO2 lasers at the time. But also for the welding, we applied also some donut shape or thing like that, because each type of application has a different beam shape, of course.
And do you think it would be possible to implement your beam shaping system into a commercially available powder bed fusion system?
In fact, currently within eShape, they don't use our beam shape DOEs, because we don't supply a complete mechanical head. Okay, we just supply the diffractive optical element that has to be integrated on the machine. We are just a micro-optic company. But anyway, coming back to our capability, we are able to provide these DOEs. For instance, for TRUMPF, we made a specific DOE that TRUMPF integrated in their CO2 laser cutting manufacture machine. They develop a specific head adapted to their head. So we won't have the mechanical competency, I would say.
Okay. So probably you will do this then together with the suppliers of powder bed fusion machines, I think so.
Yeah.
But we haven't.
You can discuss later on the details. I will put you in contact, Thierry and
again, the project is called InShape, INSHAPE. And you will have all detail on the website.
Yeah, that's fine. Yeah.
Okay.
Perhaps you can also write it in the chat.
I can write it again. The address of the
everybody's aware of the project.
Yeah.
Okay. So thank you very much for your question, and also
thank you very much
for the nice presentation, and also for placing your needs. And we will move to the next speaker. So we have Bernard Revaz from AMiquam, CEO of AMiquam. I'm going to help you with the presentation. So I'm sharing now your slides. Let me put it in presentation mode.
Thank you,
Bernard, the floor is yours.
Can you hear me?
I can hear you.
Very well. Thank you very much, Antonio. My name is Bernard Revaz. I am speaking from Geneva in Switzerland. The company is called AMiquam. It's a startup from EPFL and a former company we created 10 years ago, which is called Sensima. What is different about what I'm going to present is our expertise in non-destructive testing. And I would like to thank Fernando, who has been perfectly introducing our topic. We want to integrate into machines monitoring systems that go from process monitoring towards part inspection. I would like to thank also Pulsate. So we have been working 1 year in the frame of Pulsate, together with our partners IDECO and MISA, and with the support of Agnė. I want to say that this project was very important for us because we started about 2 years ago, and this was the first organization that recognized our effort and gave us some funding support and helped us also go towards the industry. Can go to the next. Antonio, can move forward. Antonio? I cannot hear you, Antonio. Yeah.
Hello, do you hear me now?
Yes.
Let me try sharing again.
So again, thank you to Fernando for the perfect introduction. Our project started, we are an NDT company, and we are developing advanced tools for non-destructive testing with a focus on complex problems. Complex problems in NDT in general may be underwater inspections. They may be going into very confined environment in a turbine, for instance, measuring complex defects. And 2 years ago, we identified that our portfolio of solutions, which are NDT equipment and softwares, would be very useful for metal additive manufacturing. And I'm trying to summarize here what is the problem. Again, has been very well introduced before. Metal additive manufacturing, if you look at the value chain or the cost structure, is not so much about digital. There's a small fraction which is digital. But there's still a lot of efforts which are required after the fabrication to have the part that can be delivered. And for example, the testing and quality assurance and inspection of parts accounts for something like 30% of the cost. And our goal is very simple, is to bring this testing inside the machine so that the certificate can be issued as early as possible, if not just at the end of the fabrication process. So you can go to the next. And so today the hurdles in terms of the deployment and wide development of the technology is related to the fact that additive manufacturing is a technology for advanced parts, like demanding parts in terms of criticality. It may be in the medtech, it may be in the aviation or space. And so the quality is something that has to be taken care. And today, the quality inside the machine is taken care through the qualification process that involves a lot of different steps. And but there is today no methods that are able to reliably and compliant with the compliance to detect defects that are below the surface. A lot of technique can take care of the surface, of the melt pool quality and properties, but not of defects that are below the surface. So our proposal is to use low frequency electromagnetic waves, also called eddy current, to probe the response of the material at depth, something like between 0.5 and 1 millimeter. So you all know, like laser powder fusion thickness, the thickness layer is in the range 20 micron to 100 micron. So if you can probe the material down to 1 millimeter, you will probe several layers, and within these layers, you can detect defects. Now, the most important is that we are not inventing a technique. We are bringing an existing technique, which is called an eddy current, which is well established in the metal industry. We are bringing this technique inside the machine. Next. So what is the technical challenge to do that? The technical challenge relies on the fact that additive manufacturing chambers, so deposition chambers, are a confined environment. It's relatively restricted. It may be also ATEX environment. Oh, I see there are some issues with my presentation then. It's a confined environment. So you want to enter into the machine. And it's also nice, the description we had before with Silios about working with the laser beam. We want to do something similar, is to add some hardware in the machine and enable new functionality to be new characteristic of the part to be measured during the fabrication. So you can go to the next. So this is showing where...
I'm sorry that I need to share like this, but I think the problem is the full screen.
Okay. Oh, strange. I had the same problem on my computer. I hope the PowerPoint is not corrupted, Antonio. So you can keep this. This is perfect. This presentation mode. Oh, sorry, the editing mode. So this is the tool that you see on the left. So this is an instrument that is attached to the recorder. You see several integration on the right. We work with most of the machines, so we succeeded in integrating our system in most of the machines. The challenge for the integration is to keep the machines and the process unaffected by the presence of the system. And what is the system about? It's about an electronic module. Here it's in red. And attached to the module, you have the sensor, which are on the bottom. And the sensors are flying over the powered bed without touching it, while the recorder is spreading a fresh layer of powder. So the system is completely using the process. So we are not slowing down the recorder. We're not affecting the airflow, the gas flow, inert gas flow. We're not touching the powder. So the system performs and works as designed without our system. We're just adding some information by having the sensors flying over the part. Something also important is that everything you see here is based on semiconductor process. So it's ready for production, or let's say a certain volume production. And as you know, this is not the case for all NDT techniques, which require very specific equipment or electronics or sensors. So we can go to the next. So what you see here is our roadmap. So the first product is a 2-channel system. And so as you understand, we don't have the coverage of the full build plate with the 2 sensors. we are measuring two lines along the build plate. But we see that there is an interest in the market to have these sensors because they are the only sensors available that can measure the material properties and the presence of defects under the surface. So we have this product W1 with a certain number of sensors, up to 4. And the second product that you see here at the center of the slide is the W2 NDT. So this is a real NDT sensor. I'm going to show you some data just after that, which is designed to have the coverage of the build plate. And finally, we want to integrate this data into a certification as a service platform where inspector could review the data and issue the certificate about the part that has been manufactured. So I'm going to show you now a few pictures, and that will be it for my talk. So we claim that this is the first part. This part that you see at the center is parallelepiped, which is 14 centimeter in length and 4 by 4 centimeters in the other dimensions. And inside this part, if you go to the next, Antonio. Yeah, and next, please. Yeah. So inside this part, for certain reasons, our customers wanted to have certain defects by design. And then we have been scanning this part during the fabrication while the recoater is moving on it by adding a small feature, mechanical feature. It's the displacement of the sensor that you see here. You have two sensors, the blue one and the red one. And the sensor have been displaced each time the recoater was moving by a certain length along the Y direction, and then they would go back to the original position. And this enables to fully monitor this part in its volume, as would be expected by an NDT technique. And Antonio, you can just flip the next 6 slides, which are cross sections of this part. You see on the top the green part, and you see the cross section plane, which is displayed in blue. And on the bottom, you see the C-scan, as we call it in NDT, which evidence like a certain number of defects that have been designed into this part. And so with this type of measurements, we really enter into non-destructive testing and the possibility to test the part. And a lot of things have to be discussed, but I wanted to present here the fact that from the technology point of view, we are not far at all. Now the question is how we integrate that into the procedure, how we can talk to level 3 NDT inspectors in your companies or partner companies to discuss that with them, and also how we can interact with the OEMs. We talk to most of them now to make this possible. Thank you very much for your attention.
Thank you very much, Bernard. And sorry for the presentation. I think your message is clear. So you have a question from Amin, so please.
Yes. Hey, thanks a lot for the insights. I was wondering what's the minimum lateral resolution that you can obtain with such a technique. In our case, I'll present that later. We print lines that can go from 1 micron to 50 micron for metals. Do you think we can see those lines and reconstruct them somehow with your technique?
So sorry, what is 1 micron? Can you tell me?
The lateral resolution, the width of the line.
Okay. So the sensor probes a surface which is about 3 millimeters, so it's large. Okay. So one position, if the sensor is on top of the surface, it will probe locally. So it's a local probe, a volume which is about 3 millimeters in length, and depth which is controlled by the penetration depth. Now, within this volume, you can detect small features down to about 50 micron. This is what. So this is large compared to certain requirements. But one problem we have is also to manufacture this feature properly to enable the validation of the technique. We realize that our partners have some difficulty to create on-demand features which are below 50 micron. It's difficult, but maybe you master this
Yeah,
You have the
actually
skills to
50
do that.
micron is the biggest we print. So
Okay.
Yeah.
So this is more like micro fabrication. Yeah. So
Yes,
this is very interesting, but I would say this would require completely different sensors, but it will be very interesting to discuss. Please contact me after the meeting.
Yeah.
I'd be very glad
Sure.
to discuss other applications.
Okay. Thanks.
Thank you, Amin.
Thank you, Amin. I don't know if there is any other question for Bernard. If not, Optocraft. So Christian, please.
Yeah, hello. Bernard, do you manufacture the eddy current sensors yourself, or do you buy them from suppliers and integrate them into your system?
So this is the key. Actually, when we started this project 10 years ago, we decided to master the full chain, including the electronics. Maybe this is even more important than the sensors. So big customers in the metal industry, Alstom, General Electric, they were coming to us and saying something is lacking in the NDT equipment because we cannot miniaturize, we cannot parallelize the systems. And all the NDT equipment is based on a relatively conservative electronic design for good reasons that we can talk about. And so we were quite a unique company in going that far in the redesign of the electronics. And actually, we have now a chip, which is 2 by 2 millimeters, and that contains all the blocks to perform a 2-channel eddy current compliant inspection. And actually, this is the reason why our competition will have problems. We know that a lot of people tried to put eddy current in the machines, but the equipment was too bulky. So, and we are the company who can really miniaturize, really down to nothing, the equipment. And what you saw actually is more like the cables, the connectors, and the battery, and the Bluetooth. But the core of the electronics can be massively miniaturized with our electronics. Mm-hmm. And the sensor, we do them, it depends. Sensor can be, certain components can be bought, or we can manufacture them. So it depends.
And you would also be able to maybe use an inductive sensor, which would maybe work also?
We use inductive methods, so we use coils basically, but we could also have a solid state sensor and a coil for the interrogating field. There are a lot of different combinations at the sensor side. And on the other side, this is our electronics, which reads and controls this sensor. Sure. So yes, there are other configurations possible, and it depends on the project. Now we have something relatively simple as what you saw is relatively simple, because the challenge was really to enter into the machines. The challenge is not yet the optimization of the sensor, but it will come down the road. We'll come to the point where we need to make better sensors because the specification is more complex.
Okay, thank you.
Thank you, Christian. And in the meantime, there was a question also from Wolfgang. What's the physical principle of your technique? It is an eddy current method. So I think you already answered the question.
It is eddy current. So invented by Maxwell or Faraday, and first used in the industry during the Second World War to inspect welds. So it's an old technique with old principle. And we like that because if you invent a new technique, before it gets into the codes and standards, it may take a long time. So
you need to prove that it's working, right?
As you know, we prefer to use old ones. But still, there were quite a lot of improvements to be done, but not on the side of the principle of the technique, more on the side of the integration.
Mm-hmm. Okay, very good, Bernard. Thank you very much, and thank you for the interesting presentation.
Thank you.
I think it's time to move to the next one. Our next presenter is Agnė Butkutė. Sorry for the surname. Senior Researcher, Head of Research Group at Femtika, and she's going to present their laser-based hybrid microfabrication solutions. So, Agnė, the floor is yours.
Okay, thank you for introduction. I hope that you can hear me well.
Yeah, we see the presentation.
Well. Yeah, I will repeat. I'm Agnė Butkutė from company Femtika. In Femtika, actually, I'm leading contract research service team, and right now we will be switching to slightly different topic than the previous presenters, because I will be talking about microprocessing of transparent materials, and I will be talking about microfabrication. So you will see that the scale will be much smaller than the previous presenters, but first maybe let's start with a few words about Femtika. So Femtika is quite a small company, is around 30 people company. We are located in Vilnius, Lithuania, and actually we're a spin-off of Vilnius University. I think tomorrow we will be celebrating 10th birthday, so happy birthday to us. And then let's start from talking about the main topic, yeah. And so in general, Femtika provides femtosecond laser-based microfabrication solutions. So in general, by using a single laser source, we're able to do a few different techniques. So just by tuning the laser radiation intensity, we're able to do multiphoton polymerization, which is actually additive microfabrication technique, which allows to fabricate 3D structures out of polymers. By increasing radiation intensity a little bit, we're able to do selective glass etching, which is actually a subtractive microfabrication technique, but in that way we're able to do arbitrary shape structures out of glass. And with a higher intensity, with the same femtosecond laser source, we're able to do reshaping, so some kind of ablation, marking or structuring of various materials. So all these three technologies are combined in a single workstation, which is called Laser Nanofactory by Femtika. This workstation is equipped with femtosecond laser source, of course, very high precision positioning stages and galvo scanners. And this machine are suitable for all these three types of microprocessing. I would like to talk a little bit in detail about a few of these processes. So first of them is multiphoton polymerization. You can see in the animation that just by using focused laser beam, we're able to inscribe modifications in per polymer drop. In general, we're polymerizing material in the volume. Later, we need to develop it by using organic solvents, and in that way, we're able to produce unlimited 3D architecture structures out of various polymers, which can have quite high spatial resolution, up to 150 nanometers. So as you can see that the possibilities of 3D architectures of the structure is quite wide. Using the same system, we're also able to do different techniques, so which is called selective laser etching. In this way, the process is quite similar, but we need to inscribe nanogratings inside the volume of glass, also by using focused femtosecond laser beam. After that, those inscribed nanogratings are etched in aggressive etchants such as KOH or HF. And in that way, we can do, again, various 3D shapes in the glass. Usually, we're using fused silica glass, where the surface roughness could be down to 200 nanometers. I think one of the most unique feature about this is that we're able to do internal channels inside the volume of glass. So that means that we do not need any additional sealing process. And this technology can be applied from the structures from micrometer scale to wafer size, wafer scale production. So as you can see, for microfabrication technique, multiphoton polymerization is additive, selective laser etching is subtractive technique. However, the possibilities are quite similar. So in the picture, you can see a 3D filler molecule model. One of them is fabricated by using multiphoton polymerization, another is produced by using selective laser etching. So that shows quite unlimited architecture of these techniques. Also, one of interesting feature of these techniques that we're able to produce even movable structures which does not require any additional assembling process. So here you can see polymeric structure, which was just polymerized, and you can see that the tentacles of the squid is moving freely in the water. Another example is glass structure. This is called Geneva mechanism. Again, structure which was made directly out of single piece of glass. Just by inscribing the modifications, so we place the magnet on top of the mechanism, and the whole mechanism is placed in external magnetic field, and that way the movement of the structure is kind of automated. So this just represent the possibilities. This kind of represents that these techniques are quite suitable for various micro robotic solutions. Of course, the applications of these techniques are quite wide, starting from the sensors to micro-optical components, such as, for example, lenses. Here you can see Fresnel lens, of course, photonic crystals. Also, multi-photon polymerization technique is suitable for scaffolds, manufacturing, for cells growing. Also, for example, here you can see the nozzle made out of glass. Here you can see the channels fabricated inside the volume of glass. And of course, these techniques quite good for microfluidics. Here you can see that that example of hybrid microfabrication, because hybrid means that we're able to use a few different techniques in a single device fabrication. So for example, this is extremely valuable for microfluidics, where we need, for example, to fabricate the channel. The most efficient way to fabricate the channel is just to remove material from glass. So this is the ablated channel on the surface of glass, and later we can integrate very precise polymeric filter suitable, for example, for filtering. Another example of lab-on-chip device. So this is a microfluidic chip which was created to serve as a liver-on-chip. That means that this microfluidic chip is consists of 3 separate channels separated by pillar-type filter, fabricated together with a channel out of glass. And the center channel, we tested it with liver cells. The liver cells was grown in the center channel, and that way we're able to testing how real tissues reacts with different solvents and different materials which can be introduced from the side channels. Of course, this device also can be called hybrid, because here we needed to connect a few different techniques. So one of them is selective laser etching to produce the channels on top, but of course on top we needed to encapsulate this device, and for that we use a laser welding technique. That means that we welded the cover slip on top of the system and just seal the fabricated channel system. So as you can see that the possibilities of these technologies of that hybrid fabrication is quite wide. So if you have any crazy ideas, please contact us, and yeah, we will be waiting for your challenges. So thank you for your attention.
Thank you very much. Yeah, really interesting summary of all your capabilities, and we already have a question, Amin, again.
Yeah, coming up with a crazy idea. Thanks a lot for the presentation. For that nozzles that you were showing in one of the last slides, what's the smallest you think hole you can achieve?
Usually when we're talking about selective laser technique, that we are kind of limited with the aspect ratio of the channel. So usually in the glass, we're talking about the precision of single micrometers, but if the channel will be quite long, that means that we will not be able to achieve a single micrometer resolution. Yeah, but if we're talking about quite small structures, then even a single micrometer could be a limit.
So you think you can make a tube out of a nozzle that would have that shape, that has a 1 micron diameter?
Yeah, it depends on the total length of the channel, but imagine that the aspect ratio which we can achieve easily can be 1 to 200. So that means if we have 200 micrometer substrate and we need to fabricate a channel through it, that means it could be 1 micrometer. Yes.
Okay. Thank you.
This is kind of the limit, yeah.
Yeah, it's a good limit. It's a good limit. I'll probably try to talk to you afterwards.
Definitely.
Any other question for Agnė? I have a curiosity, and it's about, you show some applications in microfluidics, but did you try your techniques not only, you mentioned glass, but in a biological sample? Do you have any idea of going or trying these kind of materials?
In general, some of these materials was tested with biological samples because the polymer which we're using is kind of biocompatible. Again, the last chip which I have shown to you in the presentation was also tested with the real liver cells. Of course, the glass is actually biocompatible, but for real cells to grow there, they need, of course, different layers of some kind of hyaluronic acid layers and so on to grow in the chip. So in general, yes, we have a little bit of experience with the biological samples.
Mm-hmm. Very good, very interesting. I don't know if there is any final question for Agnė. If not, thank you very much for your interesting presentations. And we move to our next speaker. We continue in the two photon polymerization, and we go now with Robert Kirchner, he's co-founder and CEO at HETEROMERGE. And he's going to present the functional 3D microprinting, the power of in situ material exchange in 2PP. So Robert, the floor is yours. We see the presentation already.
Okay, great. I hope you can also hear me.
Thank you. We hear you.
Great. Thank you very much, Antonio and EPIC, for giving us the opportunity to present our company, HETEROMERGE. It's a very long title. Maybe to make it short, we are also talking about two-photon or multi-photon polymerization. We're talking about polymers. We're talking about micro additive fabrication, so very small structures. And our key component, what we bring, is we bring functionality, and we mean functionality, we mean different materials. So we bring an exchange of the printing material on the fly for this two-photon polymerization or multi-photon printing process. Maybe a short word on HETEROMERGE. The project started as a project already in 2018, but we are legally incorporated only since this January. So we are a very young and fresh startup of the TU Dresden. We are 3 co-founders and we have 3 more employees. So we're very small, 3 in total at the moment. So let's have a look on what is driving us. And when we talk about functional printing, so let's start with something everybody maybe has seen somewhere in their history, is a macroscopic objective of a digital camera, and it gives beautiful images. And it gives it because it has these beautifully polished glass lenses of different materials and different shapes, together with mechanics, all stacked in a housing. And this gives super nice images. And then we said, I think we can do the same thing again, we as a mankind. And we made the same thing, very similar, for micro or millimeter scale optics in our smartphones. And we do the same trick. We injection mold glass or polymer lenses. Now the shape gets a bit more crazy, more aspheric to deliver the optical images. But still we take discrete components, assemble them together in a barrel, mount them, and that's it. And we have good image quality. The thing is, we always want to go smaller, and the next step is go for really micro optics that could be on a optical fiber and form a super small endoscope. And here the problem is, slowly it gets challenging. You cannot pick and place these very sub-millimeter, hundreds of micron lenses, assemble them. And to get a good quality, you still want to say or play the same tricks. You want to use different materials. Now the thing is, you cannot use different materials in this printing process so far. So you are basically limited in the optical quality. So doing chromatic correction and focus improvement by composite optics is very challenging. And what we try to provide is a solution for this issue. And we see, if we wrap it up in a broad view, where's the applications? And we see these in medical imaging. I think I mentioned that. So a very small endoscope on the tip of an optical fiber, so diameter of a human hair that can basically go in the smallest arteries of the human. But also smart glasses that do not look like smart glasses, they just look like normal glasses, but have the optical engine and everything integrated. And they are so small and compact because we have a fabrication technology, printing for these optics of different materials that can make a very compact optic that is very resourceful with the photons, so really is efficient. And the other thing is we're also using every day, basically without knowing it, is the data centers where from optical fibers, data is converted to electronic chips where it is still processed and computed on. And what we want to have is the fibers to come closer and closer, ultimately directly onto the chip. So we need very small integrated optocouplers that are very high efficient. And this is where we see printed optics and printed optics with different materials to play a role. Now, the good thing, and thanks to Agnė for the nice introduction, that I don't need to explain the technology that is behind, but just let me show you this picture. We will see this again, and it's important to understand. So what we have in this case is a 780 nanometer laser focused to a high magnifying objective into the liquid. So we are working in immersion. So here the objective is immersed into the liquid, and in this focal point called the voxel, the curing element, above the threshold, the polymer cures, and you have basically a very fine pen you can draw through the polymer and make a freeform 3D structure. So far only with one material, but the quality of the prints we saw also before is superb, is crazy. And it was used a lot for mastering. It is used a lot for mastering optics. You create a master structure, you replicate this into a working stem, and then you replicate this further into your working material. And you can be very cost efficient by that, because you can do this in a mass production. The challenge is if you want to have superior optical functionality, you need different materials. And so far, at least, there's no way to do a replication with different materials. What you can do is stacking, but as explained in the beginning, if you want to stack very small elements, it gets really challenging. So what we thought is we take this droplet, we have the objective immersed, so we focus the laser into the material, and we print. This is a dummy structure. This is a church here. You will recognize later again. Up to a certain layer, so really print layer by layer. You print the structure up, and at a certain point, you decide now it's time for a new material. It will be the cupola for this church, or can be another lens in your lens stack, or can be a mechanical structure that supports the lenses, or can be a black aperture that blocks stray light, etc., etc. So what we do is we inject liquid. This is now the key thing. We have a print head. So we inject the liquid into this droplet basically, and synchronized, we remove the excessive liquid. So that means if you look on top of it, this is and you will see and understand it's a very small scale printing. This is an objective about 40 millimeter in diameter, and we have a liquid droplet on top, and we inject to see it better here, the red liquid. It is passing through until the exit. So down here's the entry, up here's the exit. And after a certain time, all the materials exchange. And now the key is the laser in principle that is working here. It does not know anything about this material exchange. It was just switched off, materials exchanged, and now the printing just continues. So it continues basically where you stopped it. This is the key point. You print in a different material. Top part is a different material, a lens or something else, but the lateral alignment is perfect, nearly perfect, because you just continue where you stopped. There's no relative movement between the printing substrate and the objective. So, and you can start over. You start with a third material, or you go back to the first material, depending on your needs. That's not just a vision, it's really existing. And here's the key point. You're not making printers, you're making print heads. And you can imagine this a little bit like desktop printing when the color printers came across many years ago. You plug in your cartridges with different colors. And basically what you do is you have a print head that also plugs in different materials, different colors, if you want to say so. So what it is in this system, that is what we have in our lab we are using, is the nanoscribe GT2 system. And this is what comes from us. This is the electronic box that regulates the pressure and the vacuum. Obviously, you drive the liquid into the print head with pressure, and you remove the excessive material with vacuum, because it's an open fluidic system, and there's more advantages of that. I will cover that later. So what is inside is basically more interesting and the magic. So this is the patented technology. So we have the reservoirs inside the system. So it's all very, very convenient arranged. The liquid is coming from the reservoirs onto the print head. And that is how it looks like. So we have mounting plates down here for distributors, for flow sensors, for valves, for clamps, etc. And what you see here is now a prototype in a 3D printed material, but it is for the customer solution, because we are changing a lot with the design. But for the customer solution, it is in aluminum. And we have these needles on top, and it's a slightly different design. You will see in the video soon. But basically, we have injection from the right side here, and then extraction from the left side. And this is the objective, the stainless steel that comes with the tool. And we just mount in an efficient way the printhead, and can be removed anytime if you don't want to use the printhead. So if you would zoom in, you would see the process you saw in the picture before. In this way that we inject now the material. Now there will be printing, but there's no printing. We exchange directly for the next material, now the transparent material. So you can cycle between, in this case, transparent and a red material. The red is a laser dye, and you can go back and forth and sequentially print different segments of your complete structure in different materials. Now, what I mentioned already is there's a key benefit. Of course, it's automated, and the gold standard so far is manual exchange of the material. So we think we're about 10 times faster with this automated process. And of course, it's also less resources, labor resources needed to do the exchange. If you have a very precise piezo that keeps the system at ±10 nanometer accuracy positioning, you get about 100 times more precise in placing these, example, the red cupola on top of the blue basement. So that means down to 50 and below nanometer placement accuracy. And what you see here is basically where red and blue meets. This is here where you see these openings, windows in the real model. There's absolutely no lateral shift. You see no lateral shift because it's perfectly placed onto each other. So that's the best thing you can potentially do with joining the prints together. And I mentioned before, it's a substrate independent solution. So wherever the laser printhead or laser goes, our printhead will follow. It's an open fluid, so we can go on small structures, we can go on large wafers, up to now 100 millimeter. This is large for us, because that's what the system provides. And it can be also active devices. It can be on edge emitting lasers, can be on vertical emitting lasers, can be on LEDs, can be onto optocouplers as connectors. So it can really, because it's open, you go basically everywhere and print everywhere. So just because time is running a bit short, I try to summarize. I give you 2 examples I can share here at the moment from first customers. So the system is in a pilot phase, a prototype configuration where we have a few customers that are testing the system and jointly developing together during this year. And from next year on, it will be available for, say, everyone that is willing to test the system. And one of the very first pilot customer was the University of Stuttgart at the Force Physics Institute, Professor Harald Giesen. And we are very happy that we are allowed to share some of the results here that are going to be published soon. And what you see here, basically, that's why I had to skip a bit forward to see like a negative pyramid printed section down here. And you have a pyramid with a cone printed into this negative pyramid. So what you see here in the top view in the printing is basically you look into a bowl or into a depression that was printed from the first material, commercial material, IP dip from nanoscribe. And you see that right now washing out this IP dip by IPS is a different refractive index material. That's why we want to combine it. And you see the stream of material going out. So the injection is from left bottom to top right. And you see over the course of time, this disappears. And at some point, all the material is washed out. And now you can print this top part with the cone and the pyramid. So it gives an achromatic hexagon. So basically, it's a rotational symmetric system that basically like a prism, a rotational symmetric prism that will split. Usually it will split the light into the colors like a rainbow. But if you have an achromatic hexagon consisting of 2 materials, so that's a condition, you need 2 different materials put together, you get color corrected hexagon in this sense. So it demonstrates that with this high precision of printing the bottom part, changing the material, printing the top part, you can get a broadband chromatic correction for this optical element. And that's very interesting for many optical applications. And as a last example, what I like to show is another one that's not optics, a little also to inspire your idea. This is for medical and bio applications. What you see here is an array of 7 by 7 very small micro needles, where the pedestal part is printed from the commercial material IP tip from nanoscribe, and on top we print a laser color or laser dye doped own solution, a PETA material with the dye. And what you see here from the SEM insert is a perfect match of the top cone onto the bottom part. So this is very interesting for applications for transdermal microneedles or for drug development, tissue engineering, where I want to print different materials. So far, we are talking only about different optical or refractive index materials. We can also think about stiff materials and rigid materials, biocompatible or non-compatible materials, or cell-loving, cell-non-loving materials, hydrophobic, hydrophilic. We can combine many, many different materials in one print, and there's one advantage that we join them basically in situ together. So to wrap up, I think that we saw 3D printing is there in industry, and we think two-photon polymerization or multi-photon polymerization will be in 2 to 5 years. It's now entering industry, optics fabrication, and with multi-material, it gets even more opportunities. We think it will move soon to industry. So we developed this add-on to existing printers. So we provide this add-on and this system that does the material exchange. And what we offer is the full system, the full technology, and also the service during the existence, of course, of the tool. And we also offer for the early, guys that want to enter this field and don't have our own printer at the moment, but that is for the product very interesting. We offer feasibility studies together with these potentially new customers. We do process development, joint development, materials testing to help to get started with this technology to create a low barrier entry. So what you're looking for is exactly for these partners that are interested in micro additive polymer fabrication, combining different materials. At the moment, we are very much, because we're coming from the optics photonics driven in this direction, but we are eager to expand our knowledge and partnerships into other fields like bio applications, MEMS, materials, etc. So thank you very much for this opportunity. Again, Epic and Antonio, and you're open for any discussion or reaching out at the end after the talk by email. Thank you very much.
Thank you very much, Robert, for showing us your approach. I don't know, we have already one question. I don't know who it's anonymous attendee, but he's asking what's the available material spectrum up to now?
The available material spectrum, okay. And this is a very, very good question. So as I said, at the moment we're working with optical materials, and we are having this the nanoscribe system we tested and screening at the moment basically all the commercial materials we have available. That is all the commercial nanoscribe materials. They are working. The time to change depends on the material combination, and we are testing also almost their materials at the moment because they're very interesting. They are known to be industry standard materials like Homo core. They can be reflow soldered even. So this is what we are testing, and we're looking into some hydrogel materials that are not fully tested by us, but we are starting with this. So basically the field is very broad. And we have the most experience with the commercial materials at the moment. So if you talk about the refractive index, it spans from at around 600 nanometer wavelength, from 1.47 up to 1.62, and from very flexible to very rigid, from swelling, hydrogel swelling or non-swelling. So it's a very broad spectrum, and we see also the development in materials now coming up, more and more new materials being added. I think this is like in the big brother, the 3D printing, additive fabrication, where materials is today everything.
And I have a question regarding the integration you show with the nanoscribe machine. Is there any processing tool that can check what's the processing, or do you have any inspection process, or?
That's a very good point. What we provide also new to the customers is like an on-site surveillance camera that monitors the print side, and from this we can really monitor the process, how the exchange is going, if it is going well, or if you have to tune it. So we do it's a very simple process. It's just a camera overview, and we plan in the future more computer vision. We have a colleague that is specialized in computer vision, integrate that as well. But Our monitoring is basically by flow sensor, so we see how much is flowing, and by a camera that so looks on the complete printing scene. Also makes sure the tool is in a safe operation state because we're handling liquids inside.
Mm-hmm. The camera is just a visible camera, typical
Yeah,
RGB.
Is an industrial camera for visible range, basically.
Mm-hmm. Okay, thank you very much. So if there is no more questions for Robert, thank you again for presenting your very interesting solution.
Thank you very much.
If anybody wants to be in contact with him, yes, let me know. You also saw his email address, so feel free to contact him as well directly. And we go with the next speaker. Amin is the co-founder and CEO at Hummink, and he's going to present high precision capillary printing. So Amin, the floor is yours.
Thank you. Thanks a lot, Antonio. Can you all see my screen?
Yeah.
Yeah, good.
Now it's
Awesome.
in full presentation.
Cool. Thanks a lot for the opportunity again, and for all the speakers. Very nice presentations and insights on the field. Looking forward to talk to you later on. So I'm going to present you what we do at Hummink. Basically, it's an additive manufacturing technology, but at micronic and submicronic resolutions, and we use a different way somehow to achieve this printing. So in brief, we have this technology that is called high precision capillary printing. That is very fit for display in semiconductor industry. That's our main focus, even though the definition is quite large. We also use it for other applications. And we are a spin-off from École Supérieure in Paris, and we start to have representatives in regions where semiconductor is happening. So Korea, Asia, US, and Europe, basically. And it's been a little bit more than 2 years now, and we have already sold one equipment actually for biosensor applications. So that's why I was telling there are other applications where you can find our technology that are indirectly correlated to printed electronics. Our goal is to reach high volume manufacturing capabilities by 2024 through a different, let's say, business model that will also take some time to present to you, because we consider Can you guys hear me?
Now I hear you.
Yeah, so internet just got crazy right now. I'll try to make it quick. So supposedly be able to share the presentation. Okay, so I'll show you a quick way of how the technology works. It's called high precision capillary printing, or HPCAP, and it's based on a oscillating macro resonator. So it's a tuning fork that you can find also on classically what a musical tuning fork looks like, and that constantly oscillates, and that the glass tip that is attached to it, as you can see, and the glass pipette is filled with the ink of your choice. Once you get that ink in contact with the substrate, the resonance frequency of the tuning fork is going to change, and you detect the exact moment where you have a drop that is formed between your substrate and your tip. So that's the meniscus. And once that happens, we don't apply actually pressure, no UV, no laser. It's strictly based on the strength of capillary forces at these resolutions. So you can do drops like that. So if you go up resonance frequency comes to its previous value, and you just duplicate that. So it's not a drop on demand, but rather continuous printing, as you can see. So we move the substrate below the tip, and we are able to constantly sense the substrate, so it adapts to the surface roughness and the topography of the sample, because like a blind people's canes, we are actually always sensing the surface to know where exactly it is, so it's automatically adapts to the topography and roughness. You can use a wide range of inks. We're working on multi-nozzle options, huge freedom of design. It has a 20 nanometer precision, and doesn't generate satellite drops, so it's very efficient to actually go and make repair for certain circuits that are have defects, or for just printed circuits in general. But at resolutions that can go from 100 nanometers to 50 micron, you can deposit really any ink, and those are the glass tips that I was mentioning a little bit before. We pull those glasses, and it creates different diameters, hence different line widths. So once you've done that, you can very easily change the tip. This is just a set of examples of what we are able to print, and we conceive the technology as an independent printing hand that we hope we will be able to integrate in other equipment manufacturers' machines, because we don't manufacture anything by ourselves from A to Z. So we need other people's substrates to use our technology. So I'll skip this slide, as you know now how the technology works. But as I was telling you, you have unique freedom of design with the technology. You can print silver, copper, gold, graphene, but as long as you can make an ink out of it, which makes a broad range of possibilities, you can deposit that on any surface, because we don't apply electric field. There's no polymerization. So really it works like the smallest fountain pen in the world. You come in contact and write. You can also do some small structures in 3D with like these bumps, very useful for advanced packaging applications. Waveguides that you can see on top left. The smallest waveguides period that we did is around 400 nanometers. You can make dots, and you can make also devices with very narrow gaps for increased electric field between the interdigitated electrodes. So we've been down to 300 nanometers or 200 nanometers for that. So huge electric field. So the limitations that we have, trying to anticipate a little bit that question, mostly on the ink, to understand that a little bit. The rheology, you have to consider that, even though we can go up to 100,000 centipoise. Particle size, if you have any, to prevent clogging of the pipette, but we respect the 10% ratio between particle size and the line that we deposit. So we also manufacture our own ink to meet the requirements of the technology. And obviously, since it's a capillary-based technology, surface energy is very important. So surface tension, contact angle of your substrate. And we know how to adjust these three elements to be able to make the ink that works with a presentation. And what we hope to do with this technology is we are tackling a wide range of markets, but as of today, we're focusing on what is not very high volume manufacturing, which is display repair. It's lots of displays, but the number of repair that you have to make is substantial, but we can reach that. Wafer level packaging and watchmaking, but as I was telling you, we're already also starting to make proof of concepts for biosensors and waveguides to hopefully find and learn with these markets what will allow us to reach very high volume manufacturing with the right partners afterwards. And a quick word about the business model. As of today, as I told you, we consider ourselves as technology providers. So for the low volume production R&D, we do everything. We do the equipment, we sell a prototyping tool, the inks, and the glass tips. But moving forward to the high volume production, we want to only keep a little bit of that printing module and the electronics behind it to leave for equipment manufacturers and chemists the facilities to provide licensing agreements to make the inks, but also integrate our model in their machine. That's basically how we envision our business model. So today we already have sold one machine and installed a machine also in Taiwan. An upcoming machine is going to be installed in Japan, so trying to develop the technology like that. And we have this Nazca tool, which works very good for R&D purposes. It's a tabletop small equipment that you can set up on your lab that is clean room compatible with volumes and productivity that fits really low volume productions and R&D needs. So this is what we have as a product today. I think my time is on. So I'll thank you for the opportunity.
Thank you, Amin, for sharing your approach and also your ideas for the future. We already have a question in the chat from Alain from Consultants Optap. He's asking, have you done repair of photonic integrated circuits? If so, have you got any examples of that?
Yes, well, I can show you exactly the samples of the clients, but we have been able to go on substrates that are used in repair, basically TFTs for one of the examples, and recreate interconnections with resolutions that are and precisions. Basically, that's where we are very good at to do that, and yeah, it works quite well.
Mm-hmm. Very good. So we are a little bit of we're a little bit of over the time. So feel free to contact me again if you want to discuss more in detail with Amin, and thank you very much for your presentation again. And let's go with the last speaker. Now we will talk about materials to finish the meeting today. And we have Maxime Delmet, CEO and founder at AM4AM, is going to present the production of new metal powders for additive manufacturing by cold plasma technology. So Maxime, the floor is yours.
Yes. Can you see my screen properly?
Yeah. We're only missing the full presentation mode, and we are here. Okay.
Perfect. So thank you for having me here. My name is Maxime Delmet. I'm the CEO and founder of AM4AM, a startup based on new materials development for additive manufacturing located in Luxembourg. And my talk today will be about the production of new metal powder for additive manufacturing by cold plasma technology. And I will go a little bit deeper with the use case of Hyperol, our first material. So let's have a brief reminder about the challenge metal additive manufacturing is facing in terms of material. So we could have some difficulties like reflectivity of metal powders, sensitivity to oxidation, difficult to handle powders, presence of cracks in the microstructure due to hot cracking phenomenon, batter phase topography, and also alloy decomposition due to high laser power. So basically, these challenges come from the constraint that laser-based metal additive manufacturing apply. So we can cite laser matter interaction, high thermal gradient, and reactive materials. So how we tackle these constraint and this challenge, we have developed in 2019 an atmospheric cold plasma treatment, which allowed to disperse ceramic particles on the surface of metallic powder to enhance the processability and add new properties to conventional alloy. So the idea is a continuous flux process to graft these ceramic particles. And you can see on the micrograph images, all the white dots are grafted particles. So we have a dispersion that is far better than only mixing. This is really the added value. And our technology is able to make available hundreds of conventional alloy. I will show the first one after. Also creating new alloy with design for additive manufacturing processes, because we will change by this way the reflectivity, we will build materials with that sustain the high thermal gradient. As I mentioned, it's a continuous flux, so the time of production is really short. So this allows to develop new alloy pretty quickly. With the R&D equipment we have and the production units, we are already able to produce between 6 and 10 tons a year. And cherry on the cake, this process is CO2 neutral. We are not using any solvent, any chemical, only nitrogen and electricity to produce our materials. So this technology, our technology has been applied to aluminium and especially to 7000 series. To make another short reminder, the biggest problem with such aluminium is that when you process it, additive manufacturing, you will lead to brittle parts with inappropriate mechanical properties, a lot of porosity, a lot of cracks. You can see on the top of my screen microscope image with full of defects. So it's not possible to use this kind of material to make strong parts. And so there is a huge need of new materials designed specifically for additive manufacturing. And our technology has been applied to these 7000 series to give birth to Hyperall for high performance aluminium. So basically it's the microscope images also on the top. You could see that there is no cracks anymore. Porosity is really decreased. We own exceptional mechanical properties. We keep corrosion resistance, and it's compatible with the majority of additive manufacturing equipment. If we are looking a little bit deeper about the mechanical properties, which is really interesting with 7000 series. If we compare it to the classical aluminium printed right now in the additive manufacturing field, we are nearly 2 times stronger in terms of yield strength and UTS. And if we are looking also to the main characteristic, the main order characteristic, as I mentioned, the high mechanical strength. So we delete the earth cracking phenomenon by having cooling that is really more homogeneous, with this distribution and dispersion that is completely homogeneous. Our treatment could be applied to really different kind of particles, different size also. We first choose size suitable for SLM product. In terms of reflectivity, we were able to decrease the laser power by 30%. So this is why also we make our materials and aluminium processable on the majority of the additive manufacturing equipment, not only with high laser power, and also we increase the stability because these, I would say, protective layer of particles will reduce the oxidation of our materials. So Hyperall has really been designed to sustain the 3 additive manufacturing constraints I presented at the beginning. And I was really quick to let the floor for questions, but this is only the beginning for our company. So Hyperall is now commercially available, and we are already working on other aluminium alloy, copper also, which is highly challenging with the high reflectivity, nickel superalloy, and tool steel also. So thank you very much for your attention, and I will be happy to answer if you have any questions.
Thank you very much, Maxime. So if there is any question, please raise your hand. I would like to ask you, because there was a comment from Fernando about the difficulty, or say the difficulties in aerospace to find the suitable materials. I don't know if you have any experience in the particular case of aerospace, or if you can share your point of view about that.
Yeah, there is specificity depending on the application, but yeah, there is huge different application in the space sectors, and having a really narrow possibility with aluminium. I think Fernando mentioned scalum alloy. This is one of the most used. What is different in our case is for high temperature application. I have it. I don't know if my presentation is still shared or not.
No, it's not shared right now.
I will.
But you can share it again.
Yeah, I will share it again. So in fact, what is interesting is also the mechanical properties versus the temperature. In fact, we noted that compared to the wrought aluminium above 120, we have better mechanical properties than the conventional wrought aluminium, which is exceptional. Same for UTS also, which is exceptional compared to what is on the market right now. So, from my point of view, depending on the properties required, there is space for really a lot of different alloy on the market, and pretty sure that Hyperol, that we started the commercialization 2-3 weeks ago, will find application in this sector.
Is there any process that is more interesting for your material? Let's say it's laser powered bed fusion, can be used in different kind of printings.
So in fact, it has been designed for laser based, really, to have an optimized laser matter interaction. So this is the first point. And concerning DED or SLM, right now it's designed for SLM, but there is no limitation to work and to produce something for DED, but it's not qualified yet. The moment I'm speaking, but it will be done in the near future. Okay, good.
Wolfgang, please.
Thank you for your presentation. I have one question. Is it necessary to perform a post-heat treatment for this special alloy, or achieve you the properties directly after printing?
So the property I show are after T6. So it's a classical thermal treatment. So it doesn't require any really specific thermal treatment, but the properties I show is after thermal treatment.
Okay, thank you.
Thank you very much, Wolfgang. So if there is no more questions, and we are quite over the time, thank you very much, Maxime, for showing your developments, and good luck for the next steps.
Thank you.
And I will like to finish. You will see now the poll, so please help us to improve our future OTMs. And I just have a few words about future events. Let me find my presentation. So thank you again to all the speakers. So thank you to Fernando, Wolfgang, Bernard, Agnė, Robert, Amin, and Maxime. And also thank you to all our sponsors, Optocraft and Near Infrared Technologies. Thank you for supporting our meeting today about additive manufacturing. And as I mentioned, a few words about next events. Regarding online meetings, we will have some online technology meetings, the next ones in June and July, about agriculture on laser weeding and photonics for wearables. But we are also, as you can see, focusing in other EPIC members' needs. So we develop these online marketing meetings. The next one will be in press content for photonics, and also the technology report about maskless lithography, and human resource group meeting, and a group on sustainable photonics to see how is the evolution in terms of reducing energy, using different sustainable materials. So please keep an eye on our website. Regarding next physical meetings, we will have a members delegation to Canada. You probably saw on LinkedIn the delegation to Japan that was quite successful, also to Dubai a few weeks ago. So feel free to join us in the next delegation to know the business environment in the Quebec area, and also in the area of Montreal, and then several meetings related with the laser wall of photonics. In Munich, we will have the 20th anniversary celebration, a few meetings on micro-optics, ultra-fast laser processing, and photonic integrated circuits for processing and packaging, and also the CEO exhibitor breakfast. So check our website and keep an eye of our next events. You are more than invited to them. And thank you to everybody that joined today. Thank you for this